Hi guys, today we will talk about how to solve optimization problems in calculus. They're actually pretty easy to solve. So once you get a hang of it, so every once in a while you will be thrown off by actually setting up the problem itself, but the solution itself is not very hard. So I'm going to start off with an example and solve it, but you can use pretty much the same methodology for all the problems. I'll solve one here and maybe in a different video a couple of more, and I think that should give you a pretty good idea of how to do it. So let's start with our first example. Let's say we want to make a square cardboard box. I guess it should be an A here. We want to make a square cardboard box with a rectangular sides that has 32 cubic feet volume. What dimension should the box have to minimize the amount of cardboard used? So what does that mean? When we say we want to minimize the amount of cardboard used, we are saying we want to make sure that the surface area is the amount of surface area is the minimum. So we want to minimize the amount of surface area. And this is a open box, so it doesn't have a top. So the surface area is going to be the base plus all the four sides. So what does an optimization problem typically look like? So it would have two or more variables that have to be maximized or minimized. Actually, it's a function that you want to maximize or minimize, but you want to find the variables that will maximize or minimize that function. So here are the three variables that we are dealing with in this example. So the amount of cardboard used depends on the length, breadth, and the height of the box. So these are three variables. So we want to find some values of x, y, and h so that the total amount of the surface area is going to be minimized. But then you remember, if I just want to minimize it, all I do is make a box with zero dimensions, right? So the reason why this is even a problem is there is certain constraints that are given to you. So what are the constraints? It has to be 32 cubic feet of volume. So I can make zero volume box. It has to have a volume of 32 cubic feet. And there is also a constraint on the shape. This box has to have a square bottom. And implicit in it also is a condition that it has to be rectangular in sides. So how do we go about solving this problem? The step number one is we need to know what is the equation of the function that we are trying to minimize or maximize. So the function f x y h, which depends on the length, breadth, and height. So we need to find that. And then the problem would typically give you a certain amount of constraints. So in this case, it is the square bottom box, and the volume has to be 32 cubic feet. And then what would you be asked to solve? So you could be asked one or two things. You could be asked what are the values of the variables that minimize or the maximize that function, or you might be asked to give the actual value of the function for the most optimum solution. So let's go step by step. So for our first step is we need to understand what the optimization function looks like. Step one is understand the optimization function and find the formula. So usually it helps to draw a picture. So a lot of times in this optimization problem, it helps a lot if you can draw the picture. So here my box would look something like this. Hopefully I would get a reasonable shape. So let's say the length, that is x, and this is y. and the height is h. And this is the surface area we're trying to minimize. So you have, since the box is open box, you have 4 sides and also the base you have to deal with. So what's going to be the surface area? So in this case, f x y h, x times y, this is going to give us the base, 2yh for the, let's see, pull this down a bit. So these 2 sides, and for these 2 sides, it's going to be 2xh. So that is going to be the total area that we are trying to minimize. So what did we do? Step 1, we are trying to find out what the function looks like. And in this example, this is the value of the function. And let's move on to step number 2. So this is all you have to do at this stage. So now identify the constraints that are given to us. So we already talked about these constraints, but they're very useful. The main thing that we want to do is we want to convert this function into an equation that only deals with one variable, because we are familiar with how to take derivatives when the function has one variable. But when you have 2 or 3, it gets a little tricky, and that goes into more advanced calculus. So here what we want to do is, how do we convert the variables, all the 3 variables, in terms of one variable? How can we express it? So we said it's a square box. So the length is going to be equal to breadth. So you can say x is equal to y. And what is the other constraint that's given to us? The volume has to be 32. So we already said x is equal to y. So the volume is x times y times h. So in this case, it is x square times h, because x is same as y, is equal to 32. So from this, you can express that the height is 32 over x square. So now notice that y is equal to x and h is equal to 32 over x square. So we are able to express both y and h in terms of x. So that's our step 2. Now all we do is we take this and plug the values for y and h in the original function, so that our function becomes a one variable function. So step 3. So we're going to rewrite this function f of x y h, which we originally said is xy, the base, plus the 2 sides corresponding to the breadth and the 2 sides corresponding to the length. And now all we do is we replace y and h with the values we derived in the previous step. So x times y, we would write it as x times x, plus y is again, instead of 2y, we write 2x, and height is 32 by x square. So our function reduces to x square plus 128 by x. Now minimizing this, we already know in calculus how to find the maximum and minimum. So you take the first derivative of this, set it to 0, and then find the value of x. So let's go ahead and do that. So our f of x is x square plus 128 over x. So let me write from this side, maybe makes it easier for you to see while I'm working on it. Dx. So the first part is 2x plus 128 by x square, and there's it also becomes minus 128 over x square. So hopefully you know how to do this, because you can write 128 over x as 128 times x to the power of minus 1, and x to the power of minus 1, you can use the power rule, and you can say minus 1 times x to the power of minus 2. So that's how you end up getting the derivative equal to this. So now we just set the derivative equal to 0. So 2x would be equal to 128 over x square, and that is, you multiply both sides with x square, you get 2x cube is equal to 128. So x cube is equal to 64 and x is equal to 4. We already got the value of x and we know x is equal to y, so we can also say y is equal to 4. So now we just need to find the value of, okay, let me write the value of h also. H was equal to 128 over x square, which is equal to 128 over 16. Is that correct? Oh, sorry, it was, h was equal to 32 over x square in the previous step. So 32 over 16. So that's equal to 2. So we got the value for x equal to 4, y equal to 4, and h is equal to 2. So now what's our next step? So there is one more step we should not forget. Although if you run out of time, so in some cases, I guess you could get away with it. But so what you would want to make sure is your second derivative is positive for to claim that this is a minimum.
Because otherwise, these values that you got could be the values for the maximum surface area.
So check for the sign of the second derivative, and I think I'll leave that. We're running out of time. I'll leave that as an exercise. So our first derivative was 2x plus, well, okay, let me just see if I can do it. 2x minus 128 over x square. So if you take the second derivative of that, so d by dx of this one, it would be 2 plus, this is a minus sign by the way here, 2 plus minus times minus 128 times 2 over x cube is what you will get, or equal to 2 plus 256 over x cube. So we know for all values of x greater than 0, so this value is going to be greater than 0. So this is in fact the minimum, whatever we have calculated. So note that sometimes you might be asked not just only for the values of the variables. In this case, we are asked to find the dimensions, so we are done with the problem. But occasionally you might be asked to find out what's the minimum value of the function itself. In that case, all you do is you plug in the values for x, y, and z in the function that we have initially calculated, and go ahead and calculate the value of the minimum value of the surface area. And that's, I'll leave that as an exercise because that's pretty easy to do. Anyway, hope you got to see the steps, and I'm not going to rewrite the steps here, even though it's always good to recap, because you can always rewind the video and check what all the steps are required. So I came up with 7 steps. I think if you follow that, you should be able to solve most optimization problems.